Go. Okay, so yesterday we talked a bit about circles. Bow tie Tuesday. That's right. You got your bow tie on at home? Everybody, you got to have a bow tie on. Come on, guys, don't juice me here. I don't care if you're on your couch, in your kitchen, all right, in your room. Bow tie. You know the rules. Thank you, Megan. I know I can always count on you. I know it. All right. So back to our circle stuff. We talked yesterday about kind of just some basic circle setup, a lot of review from geometry, and then kind of updating that to find general form of a circle, and then how to put that into standard form. So that's what we're doing here. Is we currently have the general form of a circle, and we want to put it into standard form. That way we can find the center and find the radius. We're going to do this a lot with a lot of our conic sections, so not just with circles. So get used to this process. First step, we're going to bring over the constants to the other side. So I'm going to add 12. I'm also going to go ahead and just group together my x terms and group together my y terms. So x squared minus 12x. I'll leave some space. Y squared plus 2y. And leave myself some space. And then I have my 12 over on the other side. Miss Hall is observing you via FaceTimes. Plural of FaceTime. Don't mess up. Well, there's no guarantee there. But hi, Miss Hall. Miss Hall, would you like to guest lecture this math analysis class? I can bring you in here on the link. From there, we're going to complete the square with the x and the x squared, and then also complete the squared for the y and the y squared. So remember, completing the square involves adding b over 2 squared on both sides. And you can't see that. Let me move that down. Okay, add b over 2 squared on both sides. So for the x, negative 12 over 2 is negative 6. Negative 6 squared is 36. So I add 36 to both sides because, of course, we always have to do the same thing to both sides of an equation. And then for the y values, or the y terms, 2 divided by 2 is 1. 1 squared is 1. So I'm adding 1 to both sides. All right, so that's just completing the square. We have to do it twice, once for each variable. Okay. On the right side, we'll just combine those together. 12 plus 36, so 48, plus 1, 49. And on the left side, we can just factor each of these individually. So x squared minus 12x plus 36 factors into x minus 6 squared. Y squared plus 2y plus 1 factors into y plus 1 squared. So now this is in standard form. This is now the standard form of a circle. So we should be able to automatically from here figure out our center, which is 6, negative 1. Right, remember, we just look at h and k here, these values, but we switch the signs on them. So negative 6 becomes a positive 6 value for the x value of the center. The y plus 1 tells us that negative 1 is the y value of the center. And the radius is the square root of 49, which in this case we actually know is 7. How was that, Miss Hall? Did she fall asleep? It was pretty boring, but was it adequate, sufficient, superior? What kind of adjectives can I get here? She fell asleep. Classic. Gets me every time. All right, so we're going to move on to our next section today. So yesterday we talked about circle. So if I cut straight across this double cone and I take apart the pieces and I look, I would see a circle. And now what we're talking about is if we cut at an angle through one of these cones, it doesn't matter, which way. So this envisions we cut like that, but we could cut like this or whatever. But the point is, if I make that cut and I pull those pieces apart and look at what shape there would be, it would be an ellipse, okay, kind of like an oval. Right? Ellipses, wonderful, wonderful shapes. I think everybody, probably one of your favorites, if I had to guess. Right? But I would doubt that you've actually known a lot of information about ellipses, in terms of like the actual equations or anything like that. We're used to working with circles from geometry, and you guys probably know what an ellipse is, or you know what an oval, oblong type shape is. But what does that actually mean in terms of like the equations or different pieces of aspects, characteristics of the ellipse? So let's talk about that. Okay, we have two different types of ellipses. All right, so the first is a horizontal ellipse, where it's kind of elongated horizontally. And that equation is this. Personally, favorite shape is a decagon. That's not bad. That's a good shape too. I will not lie. But in terms of curved shapes, I think ellipse is probably pretty high up there as well. Any particular reason why you like the decagon so much, or is it just always been your favorite, like since you were a kid? So this is my formula. Now these numerators both pretty much just come from, this is like the same part from the circle equation, right? X minus h squared, y minus k squared. But the difference now is that we have these denominators of divided by a squared, divided by b squared. And then on the right, instead of equaling some number, it equals 1. All right, and that should always be 1 on the right side for an ellipse. The way that we know this is a horizontal ellipse is because A is the larger number. And the good way to remember it is that when the larger, whatever variable the larger number is underneath, that's going to be the longer part. So in this case, if the bigger number A is underneath the X, that tells me it's going to be larger in the X horizontal direction. It'll be more stretched out horizontally. Decagon, speak to me on a personal level. Okay, yeah, I won't get too much into it there. I don't want to invade your privacy. Sounds like they're very important. So I appreciate that. I respect that. For a vertical ellipse, it is almost the same equation. Oh. Okay, I'm gonna mute this. This is my doctor. Hold on. All right. Good news. I don't have to have my arms cut off after all. Can we call them tall and short ellipses instead of vertical and horizontal? No, I don't think that works still, because you could still have like a, it's a much shorter ellipse, but it's still a vertical ellipse. You know what I'm saying? Should invite the caller as a surprise guest on the live stream. Yeah, the doctor. This stream is sponsored by well, I'm not going to say my doctor's name on stream. Never mind. But it's sponsored by them, so that's all you really need to know. And again, so the way that we use this, so the way that we know it's a vertical ellipse, A is still, so for ellipses, A should always be the bigger number. But in this case, the A is underneath the Y value. So that tells me the Y value is going to be the sort of larger direction, right? So it's longer, more vertical. Whenever I look at my shirt on stream, it kind of has like an optical illusion type effect. Can you guys see that too, or is that just me? It's kind of weird. Austin will use to find your address. That is true. That is true. Austin is more horrifying than any virus I could ever imagine. I'm just crazy. Well, maybe. I won't tell you what my doctor said, but they wouldn't disagree. Okay. So, again, the larger number, whichever variable that number is underneath, that is the larger direction. So either horizontal or vertical, depending on if it's in the X direction or the Y direction. What are you all talking about? What a great question. Okay, the major axis That was kind of fun. Okay, the major axis goes through the longest part of the ellipse. So let's say this red dot is the center. So depending on whether it's a vertical ellipse or a horizontal ellipse, we call the major axis the almost like a diameter for a circle, but it goes for ellipse since it's different. So it goes through the longest part of the ellipse. Right? These purple points here are what we would call the vertices. Okay, each of this like a vertex. We call both of those points the vertices on either side. And the way that we determine how far away the vertices are is whatever that number A is from our equation. All right, so it's A. Minor axis and co-vertices. So same thing. Let's say we start, here's the center. Then the minor axis will go through the shorter side. Okay, like this. So that's the minor axis. And the co-vertices will be those points that are on either side of the minor axis. And the way that we determine what that distance is by looking at B from our equation. All right, so A represents the distance from the center to the edge, to the larger edge. B represents the distance from the center to the shorter edge. So pretty helpful. So next up is what we call the foci. Welcome to English class. That is the plural of the word focus. Okay, so every ellipse doesn't just have a focus, it has two of them. So we call those the two foci. So let's start off. Here's the center. And the foci are 2 points that, depending on what it looks like, will be on either side of the center. And it's important to note that foci are always along the major axis. So we can see these foci are on that largest line, whether it's vertical or horizontal, either way. A pretty big application of ellipses and foci are, well, so just in general. So if I have a perfectly drawn ellipse like this, this is actually the shape that the planets traverse in as they go around the sun. Okay, planetary motion is in ellipse. It doesn't travel in a perfect circle. It's ellipse. And actually, right, the sun, so in the ellipse that the Earth travels around, the sun is not in the center. Right? The sun would not be at that red dot. The sun is actually at one of the foci of the ellipse. Right, so pretty interesting and definitely very useful for us as we travel around that bright burning ball. My Apple Pen is coming today. Oh man, okay. And then it just has to sit in the bleach for 3 weeks and then you'll be good to use it. So that's exciting. Very cool, period. So you can tell Megan's excited. Wonderful. I'm excited for you, Cassidy. I can't wait to see all the good math that you're going to do. Megan's excited. So is Malia. MJ says, I like the enthusiasts. Well, enthusiasm. Oh, I see. Okay. All right, so we can use all this information to actually graph an ellipse using our center, vertices, covertices, and foci. I'm not bullying your spelling. That's just what you said. I didn't know what it was. That was like a new word. I'm trying to learn a new word. I was excited. Do you listen to me talk ever? I mispronounce words like once every 9 words. So I get it. You won't play iMessage games. That's sad. Okay, so we're going to find all this stuff. So first up, the center. The center for an ellipse is still HK. All right, so I'm still looking at these values, and I change the sign. So +3, -1. There's my center. It is a lot of words. Right? A squared in this case, so remember A is always the larger of the numbers. So A squared is 49, which means that A is 7, right? Square root of 49 is 7. Since that 49 is underneath the Y value, then I know that this is a vertical ellipse, right? The larger number is underneath the Y value, so it's going to be larger in the Y direction. We use A to figure out the vertices on the major axis. So I'm going to start at the center, and I'm going to go up 7. So 1, 2, 3, 4, 5, 6, 7. So here's one vertex. And then I'll start at the center and go down 7. 1, 2, 3, 4, 5, 6, 7. So these are my vertices. I'll go ahead and write those down. So that's 3, 6, and 3, -8. Right? Since I know that it's all in a vertical line, so I know the x values stay the same, right, of 3, 3, 3. But the y values, so the center is at -1, but then I need to go up and down 7. So if I go up 7, I would get to 6. If I go down 7 from -1, I get to -8. So that's where all those values came from. All right, now let's look at the co-vertices for the minor axis. So b squared is the smaller of the two numbers, so that's 25, smaller of the two denominators. So b is just equal to 5. That tells me the co-vertices will be 5 to the left and 5 to the right of the center. So I'll start at the center and go 5 to the right. 1, 2, 3, 4, 5. And I'll start at the center and go 5 to the left. 1, 2, 3, 4, 5. And I'll actually go ahead and write those down. So the co-vertices, so to the left 5, so -2, -1, and 8, -1. Drawing a perfect ellipse is hard. It is, and so that's why I was stalling here, because I don't want to, we have our 4 points, so we know kind of generally what this ellipse is going to look like, but it's a tough go. But we can give it a shot here. So maybe, oh geez. That's real rough. Real rough stuff. Okay, so that's what our ellipse should look like. We're not done. We still need to go through and find the foci. Oh, wait, I forgot back here. I was too caught up in the planets. So how do we actually find the foci? Well, we do it using this. C squared equals a squared minus b squared. Okay, so note that this is not the Pythagorean theorem. Right? The Pythagorean theorem is a squared plus b squared equals c squared. But this is a squared minus b squared. And so the distance between the center and each of the foci is c. So we'll use that to figure out where the foci should be. All right, so c squared equals a squared minus b squared. All right, let's do that down here. So foci. So first I'll use my formula that I just said. C squared equals a squared, so 49, minus b squared, so minus 25. So c squared equals 24. we'll take the square root. So 24, we'll go ahead and simplify that. 24 I can think of as square root of 4 times square root of 6. So 2 root 6. Since this is a vertical ellipse, then our foci should be up and down. They should be on top and below the center. So the center started at 3, -1. So to get the first foci, I would go up 2 root 6, so plus 2 root 6. And to get the second of the foci, I would subtract. I would go down from -1. So I'll write that by doing plus minus 2 root 6. If you want to write a separate point, so -1 plus 2 root 6 in one of the points, and then -1 minus 2 root 6 in one of the other points, that's fine. And so if I actually calculate, like, for the sake of graphing again, it's okay to use decimals to get a feel for where they should go. So -1 plus 2 root 6 would be about 3.899. So up here. And then -1 minus 2 root 6 be about -5.899. So 1, 2, 3, 5. So about right here. So there are my two foci. So for foci, we use c squared equals a squared minus b squared. And then that tells us where we need to move. Based on if the ellipse is vertical or horizontal is how you know what values do I add or subtract from. Right? Because if I need to move up and down, then I add or subtract from the y value. But if I need to move left and right, then I'll add or subtract from the x value. Okay, so we have to know and intuit what our shape should look like. Let's try that again, just to make sure we have it down. So starting off, center is 3, -1. Right, and that just comes from just like what we did with the circles. And actually this is the same center as last time because I'm so creative, or because I forgot to change the center to some other numbers. Good job, me. So if I want to figure out what a squared is, I know that it should be the larger of the numbers. Right? A is always the larger. So a squared is 81. Since the larger number is beneath the x value, so I know it's going to be a horizontal ellipse, or a short ellipse as Megan likes to call it. So to find my vertices along my major axis, I'll start from my center and go to the left 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'll go to the right 9, so I'm going to have to go off the graph a little. 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't know if you can see that on the stream. That might be just off. Whoa. Let me shift over a little. Yeah, there we go. Okay, so vertices. So 3 minus 9 would be -6, -1. And then 3 plus 9 would be 12, -1. All right, so again, just be aware. I see people mess up which values you add to. Since this is a horizontal ellipse, then the vertices will be across left to right. So we don't need to change the y value there. But we do need to change the x value. We're moving left and right. So we take this 9, we take 3, and we add 9 to get 12. 3 minus 9 to get -6. B squared is our other value, 16, which means that B is 4. So from the center, I'll go up 4, 1, 2, 3, 4, and down 4, 1, 2, 3, 4. So I can write out that my co-vertices are 3, 3, and 3, -5. So again, we can see this would be kind of a very thin, narrow ellipse, horizontal ellipse. And we have to go through the horrifying step of trying to draw an ellipse. Best of luck to you all. All right, that's maybe a little bit improved from last time. I'm going to guess Cassidy didn't do it perfect this time, but pretty close. It was like 98% perfect, just not quite 100, but still really good. That's my guess. And then last but not least, we want to look at the foci. Drawing an ellipse makes me want to leave this class. It's okay. That's our last ellipse that we're going to draw here today. All right, don't worry. Don't worry. I believe in you. If you need to attend Miss Jury's office hours for ellipse-based drawing advice, maybe do so. Set up a private Zoom conference to do that, perhaps. All right, so for the foci, c squared equals a squared minus b squared. Okay, so I already forgot what was, wait, 81 minus 16, right? Okay. Oh, oops. 81 minus 16. So C equals square root of 65. What do you mean? Square root of 65, we can't simplify. 65 is 5 times 13, but that doesn't mean we reduce it. Okay, so our foci, since this is a horizontal ellipse, then the foci will be going left to right. So from my center at 3, we would want to add square root of 65 and then subtract square root of 65. And the y value should just stay the same, since all we're doing is moving left and right. So 3 plus square root 65. Again, we'll get the decimal just so we can graph it. So that would be about 11.062. So very, very close to the vertex. And then same thing, but the other direction. 3 minus square root 65. So that would be about negative 5.02. Okay, so for this particular ellipse, the foci are very, very close to the vertices. That won't always be the case. Sometimes they'll be closer to the center. It just depends on what